Okay, I'm going to talk about filters. I'm going to explain what's on the other side of your antenna and what's on the other side of your mic or your speaker. Because on the other side of your antenna is everything from down below broadcast all the way up to VHF. I'm going to start talking about VHF, but on the other side of your speaker is what you want to hear. And what you want to hear is 700 hertz tone separated from all the others. And all the others are as close as 40 hertz from that tone. So it's above 700 hertz and below 700 hertz, and you want that guy right in the middle of 700 hertz. So if you're on, and I'm going to use as an example, transmitting at 7.040 megahertz, you want to hear that guy at 700 hertz out of your speaker. And it all starts with filtering from your other side of your antenna, which is everything from the broadcast band below to the VHF band and above. So we're going to start off with the cavity filter. Now, what I'm going to try to do is I'm going to try to change this to my camera here, if possible, and it didn't work. So I'm going to leave it on. I'm going to leave it on this thing here, and go ahead and turn around and pick up my cavity filter. Now, what I really wanted to do is to show this to you, which is on my little picture on the right-hand side. But this is a cavity filter.
Break. You're going to have to sequence your slides.
I am not going to my next slide. I want to go to this picture of me holding this huge filter.
Okay.
I have a big filter right here. And this is the bottom end of it. And this is the top end of it, right here. And this is how you tune it. With this thing here. There's a plate that goes up and down inside here and changes the length of this cavity. This is a cavity, and this cavity is resonant for radio teletype, which is 146.70. And it goes in through this port right here, this UHF connector, and 1,500 watts goes into this tin can. That's why it's this big. You've got full power going into this can. And if you are blowing across it as if you are blowing across a Coke can. You blow across a Coke can and it gives you a tone. That is what this is doing. This is a filter. A great big filter. Now I'm going to go to my next slide, which is the cavity filter. Now I'm going to put this down. Before I would like to say this one is bolted onto the wall. This thing's broken along the wall. This one in the picture here I'm going to use my arrows here. The tuning adjustment is by this screw thing here. And this is screws, a plate. Now this one shows a end of the rod here. It shows a sliding in and out. And it shows a small capacitor here. That's for fine tuning. This big one that I showed you is tuned by moving this bottom plate up and down from the bottom, or this large. Somebody just coughed. Okay, whatever. But this one has a small capacitive tuning adjustment to tune that notch up and down a little bit. Now here is where the RF connector is, and here's the probe. Now this one has a small tuning adjustment, a capacitor, a small capacitor out to the side that says C2. This tunes a notch on the other side. Now this is a duplexer. So you have I wanted to be able to show you my pictures, but I can't. I've got this so I can swivel around. Now I wanted to be able to show you this is a cavity filter here, but you've got 1, 2, 3, 4 cavities here for transmit and 1, 2, 3 for receive. So the receiver is connected to this SMA connector here. 1, 2, 3. The antenna is connected to this SMA connector here. That's an SMA connector. And here's the transmitter. So the transmitter and receiver, transmitter and receiver are connected together. And the antenna is connected in the middle here. So this is a duplexer and allows you to talk and listen with your repeater at the same time. Now it could, so you have a row of them and they have a notch. And we'll talk about a notch later. This is a bandpass filter. In a couple of minutes, I will show you a picture of a bandpass filter. But this is a UHF small, low power, not big can cavity filter. Now, I'm going to show you more cavity filters. My next slide, if I can find it. Okay, these are also cavity filters. Notice that they're all different kinds of cavity filters. The one I showed you before was a big cavity filter. These are cavity filters, and these two are also tuned by sliding the rod in and out. There's a screw here, and a screw there, and a screw there, and a screw there. And that's how you tune this cavity filter. And this cavity filter, I don't know how you tune it, but you tune it. But the general idea is it's a very selective filter. Now we're going to look at the bandpass filter. See, this is a bandpass. Now those filters I showed you were bandpass, and they have a notch. Now this is a bandpass filter, and notice that it shows you a flat top here. If you properly tune those filters, those cavity filters, you may get a flat top and you may not. You really do not want a flat top. You want a very sharp single notch right here, and you want a very deep band. Whoops, went too far. You're very deep notch here, right here, for your receiver. Now, in one end, you got a between minus 140 and dB, and maybe plus 130 dB, and you have all these 70 dB notches all in a row, and that keeps your transmit and receive apart with your duplexer. And this is just a band pass, which would be used. This one says 144. What's that noise? Is that me?
If you're not doing the presentation, go ahead and.
Okay, let's carry on. Dang. I don't have any control of this picture anymore. Oh, I got to show the slideshow here, right? There, okay, now we got it. Okay, let's get back to here. Okay, you can see me and you can see this thing, and have I explained this all together? Does everybody understand a band pass right here? A band stop would be the upside down of this picture, and that would be my notch that I want to take out. Does everybody understand, as you go up in frequency, you go down this line, as you go up and down in magnitude, you go up and down here. Does everybody understand that? I guess so.
Got it.
Okay, now, I'm going to turn around here, and I'm going to show Now I can't find it. Well, I can't find it. So they set this up for me, so I just swivel over. This is my a bandpass filter for 40 meters. That's a 40-meter bandpass filter. And this is one that's branded ICE, International Communications Engineers, N4CU. It's not a real good filter in a certain respect. This is a chart. This is the bandpass that I showed you a minute ago. See the color here? S21 log magnitude. And it says this is, the loss in this is 0.51 dB. This is right here. But I can't move this thing here because I've got this, this is just a photograph. But that's 0.5 dB right here. And here is minus 30 dB. And if you can go here, here is 6 megahertz, and that's 15 megahertz. So 14 megahertz is 20 meters. So that's right around here someplace, 20 meters. So right here, it's less than 30 dB loss through the filter. So the pass is down by 30 dB. Here it's down by 0.5. Here's down. 30 isn't a lot. That is a lot, but it's not an awful lot. As long as I'm showing you this picture, I'm going to show some other things. I am very hesitant to bring out one of my bandpass filters because people do not understand this right here. This is the looking into the filter. And notice that it's the impedance jumps around. Since the filter is looking into 50 ohms, here's the 50 ohm antenna right here. That's the 50 ohms antenna, if this is an antenna plot. And here, if I go to this point, I'm at the other end of the 50 ohm plot. If I go way over here, I'm over here. If I go here, I'm way down there. And another thing about this S11 Smith chart plot, which is this right here, the same color. This is log magnitude. This color here. This is yellow. This is what do we got here? That's the log magnitude. That's the S11. That's the output. Anyway, S11 is the input. That's the input response right here. So that bounces around a whole lot. And here's the phase angle in blue. Now I'm going to switch this to the next slide. And I wanted to show the Dunstar filter attached to the VNA, but it somehow has gone away. But notice the Dunstar filter response, it shows a loss of 0.77 dB. Right here, that's 0.77. Blue here, and this is the blue, I guess, or violet, or whatever color this is. That shows the loss right here. That shows the input impedance. This shows the phase angle shift through a filter right here. Notice that this is more than 30 dB here. So this is a better filter. It has more loss. Now, if we get to my coaxial filter, that coaxial filter was built with RG174, and that much 174 has a loss of almost 3 dB. So this line right here would be down right about in here, supposedly, through a coax filter. And then we have the slide offs here. So that's my coax filter, which I may or may not show you in a couple of minutes. Does anybody have any question about this nano small? And I don't have it hooked up. There is way over there someplace. Somehow it got put over there. But it's just a little bitty box, and the filter is the Dunstar filter. and it's very similar to that ICE filter. And we have a duplexer on the back of our ham shack wall that shows 3 Dunstar filters, and they lead to the antenna. So 3 transmitters can be used with 1 antenna. That's a 10-40 antenna. Now I'm going to switch again to the next slide. Oh, there's my coax filter. That's a drawing of how it's done and what it looks like is this. Okay, I didn't have any BNC connectors, so I used taped on C connectors, and I used RF chokes to keep these, see these lines here, since they're here, they're going to get crosstalk. From here, you're going to get standing waves along this, unless you have a coax filter here and a coax filter here and here. So this has these filters are hanging off this. This piece of coax right here has 2.5 dB. Now, I could have used a lower loss coax. I wouldn't have as much loss. But this coax filter that I made, the BNCs were $2 a piece, and the coax was probably a couple of bucks. It's $5, and those Dunstar filters run a little bit more than $100. And you don't have to worry about them because they don't burn out unless you go over 300 watts with them. So now we come to where the actual filtering occurs, and this is a roofing filter. Now this is not the best presentation of roofing filter. Here we come through VHF broadcast and all the others, and you have a bandpass filter. Now, a bandpass filter could be one of those Dunstar bandpass filters. It'd be a very good filter, but usually they go into a pre-selector filter, and usually those are tuned by the computer. So it tunes the pre-selector. Well, there's a lot of stuff that gets through this pre-selector. It goes through the preamp. It goes through the fixer. It could go through the first mixer. In this case, it does. It goes through another low-pass filter and hits the bandpass filter. In this case, they're calling it a roofing filter. Now, the roofing filter could be up here. It could be any place. It could be any frequency. This one says 150 kilohertz bandwidth for FM and 60 kilohertz bandwidth for SSB, or 6 kilohertz. 6 kilohertz for bandwidth for SSB. That would be lower and upper sideband and AM. And this is the roofing filter for this particular radio, which is up at the top. I think it's one of the icons. And the bandpass, according to this, the bandpass would be right here, and here would be the upper sideband and lower sideband. So this roofing filter gets both these 2 sidebands in. We don't want that. We don't want both sidebands in. We just want one sideband. And what we want to do is just have just half of this for one sideband of the other, and even less than that with an audio filter for just the 40 hertz that you want to hear of the 700 hertz tone out the speaker. So this goes through a bunch of other stuff that bounces this around and starts to go into the DSP filters. And these are the DSP filters. There's a phase filter, and it's combined, and it goes over and goes through an analog digital converter. Now notice here it says A to D, analog to digital, and it said, well, I've got some mistaken words here. This is going through an IFM, and we've got an A to D converter, analog to digital. So it goes through here as analog, and it gets converted to numbers right here. It goes through here, and we've got these large signals, and we want to now filter out. Well, actually, we've done some filtering by running the phase shifter here and combining them. So we've taken off the other sideband. It goes through here, goes into this amp. Now here it's digital circuit. At this line right here, from here on, it's numbers. It's numbers, and this thing here says, hey, this is hitting me with too high a number to deal with in the rest of the circuitry. And it has another digital analog converter that goes back and reduces this signal through the IF amp right here. The digital analog filter, digital analog converter reduces it. So when we go through a bandpass filter, if this is now whatever it happens to be, then the volume can be controlled by the AGC here and not the AGC here. I do not know whether this AGC detector is feeding back a signal, but this AGC here, detector here, lights the red light on the IC, on the 300s that we've got, your Icon 300s, and says OVL, overload. And when the number is too high for the DSP circuitry to calculate, then it goes into overload. Now, if it was analog instead of DSP, it would go into desense. The transistors would go into saturation, and your signal level would go low throughout the signal bandpass, and you'd lose the signal. With your D-to-A converter, with your digital signal, you just lose sensitivity. So this is what is the overload light, to say that the numbers are too high to go through your digital circuitry. And that's a whole lot to be said about this roofing filter and this sequence of filters, the sequence of mixing here. Now we're going to a crystal filter. Now this is 9 megahertz filter at a 2.7 kilohertz bandpass. Now this is one sideband right here. This is one sideband. So once you get that two sidebands together, you can click off one sideband by running it through here. And that's why you have upper and lower sideband, because the way the mixers work, the upper and lower sidebands are filtered out by this. If it's up above 9 megahertz, it goes on one side, upper, and the lower 9 megahertz, it goes lower 9 megahertz filter, and the 40 and 80, it goes through the 2 pillars filter and comes out one sideband. Now, notice that there's a little block here and a little block here that says Z out 50. The input of these crystal filters is about 1,000 ohms. Now, 39 puffs is usually what is put into, it says 3. There's 39 here. It says CP, I don't know what that is right there. It's usually 39 puffs is what you usually feed the filter with. And 39 puffs for the output, and you have 39 in between them. And you line them together for a crystal lattice filter. Now, there's only 2 crystals here, and this shows 4. 1, 2, 3, 4. And it shows a block. This is a 455 megahertz set of coils to go to up convert to the 1,000 ohms and down convert from 1,000 ohms back to 455 from this filter. Now notice, this should be a roofing filter, because if you can read this, that says 10.7 megahertz. So this is a filter that's intended to be used at 10.7 megahertz, and its bandwidth is 7 kilohertz. So this is a set 2.2 kilohertz filter, 2.7 or 3, and this is quite wider right here. There's only 2 crystals, and it's quite wider. So now let's see the next filter here. Okay, now the old standby was the Collins mechanical filter. It was the filter at 455 kilohertz. There's a set of metal discs. It could be square, it could be metal, it could be. These metal discs are shaped. And if you go into Wikipedia, and look up mechanical filters, it will tell you the size of these discs, the different frequencies. And this is like a tuning fork or a bunch of tuning forks in a row. And this filter has a certain bandwidth, like a bandpass filter. So the signal goes in here, goes through here, and it comes out at a certain bandwidth. And the bandwidth is usually 400 hertz, or at least 400, 500, 250, or whatever you purchased. And they usually cost about $125 a piece, which is quite high. And now that you have DSP filters in here, you don't have to have a bunch of mechanical filters. You can reach over to your 7300 or your whatever radio you're using with a bunch of DSP, and it's hot. That's because you have thousands of transistors working in there at the same time. They're all creating a lot of heat as they work. This doesn't create any heat. This crisp mechanical filter, there's no heat loss in this filter. But in the DSP filters, there's a lot of heat being created by all of these transistors working. So, one more step here. This is an audio filter. This audio filter is probably 200 hertz maybe. It's an analog filter. I don't see the label on it. I can't read it very well. MFJ came out with these, and the toroids were out of the telephone company. And comes out of the toroids and some capacitors, and it's an audio filter. This is a digital filter. Now, this digital filter is recreated, or a digital filter is recreated in the let's find a page here. In the November issue of ARL QST, and it gives you a digital filter, and it shows you the filter response through the Collins mechanical filter and one of these digital filters. The 400 hertz band pass of the Collins mechanical filters, which is done at 455, is quite a bit wider than this audio filter runs it at 400 hertz. So this audio filter will suppress or will be better than the Collins mechanical filter at audio frequencies, the audio frequencies that you want. And that has been a little bit more than a half an hour, which is about the length of time for this presentation. Now, there have been some burbles and probably some questions. Are there any questions? Mike, I don't see the chat on this thing, so I don't see any questions.
Hey, Bob, it's Mike. I've got one question for you.
How come I can't get, okay. Okay, I see him. I hear Mike. I hear you, Mike. Hey, Mike. Hey, Mike, I don't hear you.
Can you hear me now?
Yeah, I do now.
Okay. On your transmission line filter there, we had different lengths of coax that were like quarter wavelength long. Does that quarter wavelength have to be compensated for velocity factor on the coax?
Yes, of course it does. In fact, the calculations I did with, I use the TLW transmission line a compensator, and they will come out quite different. You could use 90% or 60% for RG174. So you get quite different numbers depending on which coax you use. And you have a lot less loss than you use if you use the high quality coax, the RG8 or RG213. But it's a lot more costly. That's why my filter is only worth about $5. And if you start having long lengths of coax, they're going to be quite expensive. Now, it used to be that the high power bandpass filters were quite expensive and the coax filters were much cheaper. But now you can buy a bandpass filter for high voltage, high power, and it won't be as expensive as trying to do it with coax.
Okay, thank you.
Well, that TLW calculator is free from ARL. It comes with the antenna handbook, as does a Smith chart program, and does a tuner design program, as does a filter design program. And these are all in the discs of the antenna book that comes from the ARL. So all this stuff is free. And you can do all the calculations you want to do. Now, to go back to this coax filter, I will replace the coax in the line, and we go back to my, we go back to this. Oops. I'm not getting back there. We go back to here. I wouldn't try to build this. This shows a T connector, and those are very expensive. So I didn't use a T. I used a BNC here and a BNC here. They were $2 a piece, and I used coax for everything else. But I think if I do this again, what I'll do is I'll just use one a notch and just use a stub. Just take this whole bunch out and just use a BNC to BNC adapter here, and we'll eliminate the 3 dB loss of this right here. And I'll put that on my network analyzer and send it out a little bit later. And that'll show you what you can do. Now let's see if I can get back to whatever this cell, whatever else we got here. I can't tell. Well, I got my picture up there. Are there any more questions? Now, my only question is understanding. Do you understand? And I can't get this thing to shit. This is a mess. This is a mess right here. And this is not typical. And the roofing filter can be up around 50 megahertz or 60 megahertz. That's why they were originally called roofing filters, because they took the whole band pass from broadcast band to television and sectioned it out and threw it up so you could filter it all out at once with a cheaper filter. Rather than bouncing it down with these mixers, they have a whole bunch of mixers. And every time you get a mixer here, you get birdies. But let's go back to the end of the presentation and say we've been on a half an hour, and are there any more questions? Really not.
I got one, Bob.
Yeah.
It's Bruce. Back on the one with the coax filters, or the coax filter. I think it's slide 2 or 3. Yeah, the next one back. Is this a notch? Oh, too far.
This one right here?
No, the coax, the one you was talking about.
The quarter there.
Yeah, that one. Is that
Okay, that is a notch filter to notch out the harmonic.
okay?
The idea is to notch out the 40 meters. If this transmitter is on 40 meters, you want to notch out. I'm trying to point at it on this drawing. Let's see. Oh, here, this transmitter is transmitting at, I think it says, I don't know what frequency it says, but this is 7.040. The harmonic would be 14.080. So we want take
You answered the question.
14, huh?
You answered the question. I want to know whether it was a notch or a cavity. So it would basically take away harmonics like the second and third harmonic. So that you answered the question.
That's what I'm going to do, is take out the second harmonic.
Okay, very good.
And see, this would take out a lot of harmonics above. This is the, which one? The Dunstar? This would take out all these harmonics above here. But it's not exactly a notch. It's not the notch that you get out of a cavity filter. Or the notch you get out of that coax filter. See where it says Nano VNA Quick Start Guide? Yeah, I use that.
I think that's all the questions we got, Bob.
Okay, Steve, you need to come over here and we'll use this Nano VNA and cut this coax up and do a notch with it. Except I don't want to put in any BNC connectors on the end of that RG174.
Yeah, we'll do that one of these days.
Sometime in the future. Well, should we go back to do whatever we were doing before? Like me go back to bed? Or TV or something?
Yeah, go ahead and continue with your presentation.
Well, I thought I did end it. That's the end of it. And I just babbled on. I can babble on as much as you want in the questions and answers. But when we get to this point right here, I'm done.
All right, does anybody else have any questions for Bob? Well, I guess there's no other questions, so I guess we can go ahead and call it a night.
We did it in 40 minutes then. That's pretty good.
Yes, sir.
Hope you learned something. No, nobody said yes. Oh, good.
All right.
Yes, Bob, thank you.
Thank you, Bob.
Thanks, Bob.
I'm glad to hear some thanks.